Hello students of the Essential Statistics lecture. In this video, we will cover basic concepts that are important for understanding and learning about statistics. So what is statistics? Statistics is not just some boring mathematical subjects that you have to learn to get your master's degree, but statistics is about doing good experiments and collecting good data. So knowing about statistics helps you design good studies. It helps you collect trustworthy data and analyze your data appropriately, so that in the end you will be able to draw reliable conclusions from your lab research and publish them also to obtain your master's degree or later on your PhD degree. Being able to know about statistics also helps you to read research papers critically and spot possible mistakes other research groups have made. So what kind of data do we encounter in the life sciences? First, there are categorical variables. What do we mean by that? We mean variables that have a few discrete values that are non-numerical in nature. So for example, these could be the color of flowers. Those would then be called nominal variables because you cannot order them. Or it can be something like the weather at a certain day, whether it's cloudy, sunny, or rainy. These are called ordinal variables because they can be brought into some orders. Let's say you start by sunny and you order them in a way until rainy, so good to bad weather. The next type of variables that we frequently encounter are numerical variables. These are variables that take on numeric values, and they also come in two flavors. They can be either discrete, if there are just discretely many different numbers that these variables can take on. So for example, here you can see the number of bacteria that grows in a petri dish after somebody put his hand in it. Or they can be continuous. So here the example shows you the measurement of the quantity of rain that fell in a certain time frame. In this case, up to measurement precision, you can specify the value with arbitrary precision. If you want to visualize such variables, it's important to know what the right tools are to do so. And this is also part of statistics. So to start with categorical variables, one way to do so in a good way is to use bar charts. So in this case, you would have the distinct values that a variable can take on the x-axis. So das funktioniert nicht. Ich mache hier einmal kurz den Pointer an, der ist nämlich ausgegangen. Okay. Yeah. So in a bar chart of a categorical variable, you would have on the x-axis the different values that such a variable can take, and on the y-axis, for example, the frequency with which these values occur in your sample of the data. The height of the bar then indicates how many of a certain category were found in the sample. What is important about bar charts is that you always have to start the y-axis at 0. If you don't do that, judging the relative height of your bars is difficult and can lead to erroneous conclusions. Alternatively to the absolute number of points in any of the categories that you find in your sample, you can also show the relative frequency or the percentage of values. You just have to label your axis accordingly. If you have ordinal data, so to remind you, data that you can bring into a natural order, it helps if you order the classes according to that order on the x-axis. So here, this graph shows you some days after a surgery how often people reported pain, so the pain incidence. But what the people that made the graph forgot is to bring the different classes of this variable into the appropriate order. So it's very hard to judge what is actually happening here. While when we order them according to their natural order, so from never to always, we can see a very clear pattern. So if you have an ordinal variable, you want to show them in an ordered fashion so that any pattern that occur can also be easily found by eye. If you visualize continuous variables, you have to use other strategies. So here we have a data set of a few countries and the infant mortality rate, and we want to visualize that in a form that is appealing to the eye and lets us quickly capture essential aspects of the data. Because a table like this is very hard to understand. We can do so in a very simple way, for example, by making a dot plot. If you have small data sets, this is actually a very good way to visualize your data. So for each data point, you just make a dot along the x-axis. If you have discrete variables, you can either resort to bar charts and visualize them in a way that is very similar as you did for non-numerical variables. So here, for example, the number of children in families, or the number of families with a certain number of children is visualized, and families with 1 child, 2 children, 3 children, or 4 or more children are separately grouped. And because these are not too many distinct values, bar charts can be used to see the pattern here. If you have many distinct values, it can be better to make, for example, also a dot plot. But because you have only discretely many values, if you just made a dot plot in parallel to the x-axis, they would cover each other. So what we do is we make a stacked dot plot where we basically build little towers of dots according to all the different discrete values that a variable can take. Finally, if we have either many discrete variables, too many to show them in a stacked dot plot, or many continuous variables, then we can also show them in the form of a grouped histogram. So for example, if we have this data set here with 36 samples, it may be not visually appealing to show them as a dot plot, or not easy to judge by eye what is happening. So what we can do is we can group these values into certain ranges. So here, these ranges are 20 units long, and we simply count how many of the samples fall into each of these ranges. And then we go on and we draw something called a histogram. You can see that down here. In the histogram, it looks on the first glance like a bar chart, but in the histogram, you show the number of values that falls into a certain range in the height of the bar. When you make histograms, one important parameter that you have to choose is the bin width. The bin width can be either too narrow or too wide, and there are no clear rules how to choose the bin width appropriately. So to some extent, it always depends on your personal judgment and on the aesthetics and on the argument that you want to make with a plot. So here one could say, well, so this is a data set with the height of many people just counted, so a couple hundreds of people. And when we just look at this distribution, we can see that it varies quite a bit. So from somewhere in the high 50s to somewhere in the high 70s in inches. If we make our bars, our histogram bins a little bit smaller, then we can all of a sudden see that the data is not unimodal, doesn't have just a single peak like it appeared in this picture, but it actually has 2 peaks. For example, it could be possible that these 2 peaks come from the fact that the dataset contains both male and female participants. So this is a fact that would be hidden by choosing 2 large bins in this plot. On the other hand, when we choose to find bins, we can also get plots that are either ugly or misleading. So for example, we see here a very peculiar zigzag pattern where every other bin of these very fine bins is almost empty. This is likely due to the precision of the measurement process, where people just measured the number of inches with a certain precision, or report them with a certain precision. So going to that fine resolution, where you see this artifact of the measurement process, wouldn't help you any in visualizing the data. So probably for this data set, a bin width that is similar to this would be appropriate. So here you can see two other examples of histograms for continuous data. So on the top, an example with the size of microfossils, and in the bottom, the time interval between electrical discharges in muscle cells. You can see that such histograms can show very different shapes. While the top histogram here is more or less symmetrical, the histogram on the bottom shows like this exponential shape. In statistics, it's not only about analyzing data, it's also in thinking about how to design studies, as I said in the beginning of the video. For that, we have to consider also what types of evidence we can encounter. Let's take this example. So on July 15th in 1911, the 65-year-old Miss Decker was struck by lightning in front of her house. She had been deaf since birth, but after being struck by lightning, she recovered hearing. So this is from a news article in the New York Times from that time, entitled "Lightning Cures Deafness." Of course, you will immediately say, well, this is just a single incident. How can you conclude something as strong as lightning cures deafness from a single incident? And you're absolutely right. The type of evidence that we have here is very weak. It's called anecdotal evidence. Anecdotal evidence can have a value in that it may lead to a conjecture, or it may lead to a hypothesis that remains to be tested. But at least while we're doing science, anecdotal evidence can never disprove or prove a scientific hypothesis. Let's look at the next level of evidence. So here we have a graph of the body mass index of men that smoke, and men that do not smoke, and women that do not smoke. And we can see that for smoking men, the body mass index is somewhat higher. This type of evidence that we find here is called an observational study. Observational studies use natural groups that are not under the control of the investigator to group the data. So it's not, as an investigator, it's not in our power to decide who is a man or not, or who smokes or not. This is something that people just do, and we can just group by these attributes our data to understand something about what is happening. In this case, we're interested in the influence of smoking and maybe gender on the body mass index. But we have to be careful to make too strong conclusions, because in this particular data set, what we find, and these are the differences between the black and the light dots, is that many of the smoking men that are also slightly overweight, that they also have diabetes. So what we can have in observational studies are confounding variables that severely limit our ability to deduct causal claims from such data. So we don't know what the relationships between these variables are. Are people diabetic because they weigh more? Or do they weigh more because they're diabetic? And how is all of that related to the smoking? It's very hard to distinguish such things from purely observational data. There are different kinds of observational studies that you can do. There's a cross-sectional study where, given a time point, let's say between October 2020 and December 2020, You just sample a random sample from a population. There's also the possibility to do a longitudinal study, but this is often much more costly and requires a much longer investment. So in a longitudinal study, you choose people at a certain point in time, and then you follow them throughout their lifetime. So you not only, let's say, compare children, adolescents, and adults at a given point in time, but you start out with a group of people as children, and you track their development as they become adults. This, of course, requires you to wait until people are actually adults, so easily 15 or 20 years. Finally, there's also the option to do case control observational studies, either in a prospective sense, that you enroll people that come in the future, let's say, to your hospital, or in a retrospective sense, that you go to your electronic health records and look for people that have been at your hospital in the past. And in case control studies, you compare people that have a certain syndrome or a certain characteristic with people that do not. But because of the fact that observational studies limit our ability to make causal claims, they have often been criticized as producing many of the random medical news bits that we find in the media all over the place. But in many cases, they are also the only way to do such studies. So you may have ethical difficulties in doing an experiment. So for example, if you're interested in finding out what the long-term effect of losing a limb on the well-being of a person is, you cannot just split people into two groups and make them lose limbs at your will. This is just ethically impossible. So you have to look at people that have lost their limbs for natural causes and just track them through time or compare how this compares to a control group. Sometimes you also simply have insufficient influence to make people adhere to your experimental protocol. So for example, if you're interested in the effect of eating vegetables on children's school outcomes, it's very hard to intervene into families and really just change the diet of children. Also, sometimes observational studies are the only way to get hold of data of very rare conditions, where you just simply have too few cases to enroll them in an experimental study. And finally, and this may also be important, they provide real-world data. So whatever kind of statistical tests or diagnostic tests, for example, you develop, in the end, that they will have to cope with real-world data. And this brings us to our final case of evidence that I would like to discuss with you, and this is the experiment. In medicine, this is also known as the randomized controlled trial. In a randomized controlled trial or in an experiment, the conditions are fully chosen and determined by the investigator. So the investigator exerts complete control over what is happening. Typically, like in this example here, we have a situation where we have multiple groups and multiple treatments that we compare. So in many toxicology studies, for example, animals are used to assess the toxicological effect of certain substances or changes in the so in toxicological studies, experiments are used to determine the toxicological effect of certain substances in animals. And here, for example, the investigators used a female and a male group and a dose of 8 and 25 units and collected data how this changes a certain variable in the blood serum of these animals. Often, experiments also use a control group and randomization. So the persons are not allocated to the groups in a way that is determined by the experimenter, but they are allocated to the different groups in a random fashion. Another concept that is important in experimental studies is that of blinding, especially in the clinical setting where drugs are tested or treatment options are tested. In blinding, either the investigator or the subject or both don't know whether the subject belongs to the control or the study group and cannot change their behavior accordingly. Why is all of that important? So for example, why do we have control groups? So here we have a study that illustrates several of these effects. The study was made to assess the effectiveness of a vaccine against the common cold. There were 200 people in the study, and they were asked to report the number of colds in the previous year from memory. On average, they reported 5.6 colds in the previous year. In the current year, the number of colds was assessed by doctors, and they found 1.7 colds in this year. So this is a 70% reduction after the vaccination. So you could conclude from that that the vaccination was highly beneficial. Luckily, in that study, the investigators chose to include a control group, in this case a placebo group, that did get vaccinated, but not with a substance that was actually supposed to help. So maybe just with saline. The people in that control group also reported 5.2 colds in the previous year and had, in the end, determined by the doctors, 1.6 cold in the current year. So also a reduction of almost 70%. What this example shows is that without the placebo group, we might have concluded that the vaccine is highly beneficial, where in reality it is not. To make the application of a placebo really effective, you typically use blinding, so that the expectations of the two groups of people are the same. What you can also see at play here, so if you try to explain why was there this reduction in the number of colds from one year to the next, even if the vaccine wasn't helping anything. And one factor that could have made this happen is the so-called panel bias. The panel bias is the fact that the behavior of people changes when they enroll in a study. So people enrolled in this vaccination study, for example, could have simply dressed better or more appropriately for the weather outside and therefore contracted less colds. It's also possible that in this case the memory of the people was just faulty and that asking for the number of colds that you had last year is just not a good way to assess that. There's also sometimes the possibility to use historical controls. Historical controls, for example, are used when you want to determine the effects of a new treatment or surgery in the clinic. And you compare, let's say, the life expectancy after a new treatment with the life expectancy of patients with the same syndrome that came into your clinic in the past 10 years. While this can be done, it also has to be done with a certain caution, because of course other variables might have changed in the time since in the time frame that you use as a historical control. So for example, the general treatment not related to the specific treatment you're interested in might have improved and might have improved the life expectancy of the patients. Also for experiments or clinical trials, there's multiple ways one can conduct them. For example, there's the parallel group experiment, where just two groups, a treatment and a control, or a treatment 1 and a treatment 2 group, are formed, and people, let's say in different hospitals, these different hospitals are symbolized by the different colors, are formed, and for each patient it's randomly chosen whether they belong to the treatment 1 or the treatment 2 group. Another option would be the cluster trial. In a cluster trial, you would, for example, say, the purple and the gray hospital, they administer treatment 1, and all the other hospitals administer treatment 2. Sometimes this can be used to reduce the variance in the data. Or sometimes it's also useful if you want to make such a study, but the technological equipment is only present at one or the other place. Finally, there's a crossover trial where you have a number of people, and about half of them belong to the group that first gets a certain treatment regime and then the placebo or another treatment, while the other half gets first the placebo and then the other treatment regime. And where appropriate and ethically fine, this can be actually a very powerful way to set up a clinical study. You don't have to learn all these different kinds of trials, experiments, observational studies. You don't have to learn all of these by heart. But it's good to know when you think about how to design your study to either consult a statistics textbook or talk to a statistician to help you do so in a way that in the end you will be able to make most of your data. If you only involve a statistician or a statistics textbook or your own statistical knowledge, at the very end when all the data is collected, it's sometimes too late to make your experiment better than it could have been done. Okay, in the second part of today's lecture, I would like to go a little bit more into how the different people, animals, instances are actually allocated to the different groups in your experiments or studies. So the typical framework that we think about when we do statistics is the following. We have a population. That population is a group of entities in the real world. So for example, it could be all women in Europe. Of course, if we want to measure something about women in Europe, it's very hard for us to do that in every single one of them, because there's quite many. So what we do in statistics, we draw a sample from this population. That sample contains a subset that is manageable for us to study. So that is the sample size called N. We do so by a process called random sampling. For that, we have to know about our sampling frame, and the sampling frame is a list of all the people in the population. In many cases, of course, the sampling frame will not be at our disposal completely, because we won't have a list with all the names that are there in Europe. The sample unit is one single entity. So in our example, it would be one European woman. And the sampling technique is the way that we actually draw this random sample. In the end, we have a random sample, and we use that random sample to draw inferences about the population. So by observing a subset through this process of random sampling, we hope to gain enough insight to do inference about the population. And this is something very fundamental in statistics to be able to, that we are at all able to do that. And the mathematics of this process is what we try to describe in later chapters of this course. Today, or in this video, I would like to discuss how these samples come about and what techniques we can use for sampling. So one thing that might come to mind is something called the judgemental sample. So the researcher that wants to conduct a study, she could simply decide, based on knowledge or judgment, which people get enrolled. So if I do a study in my class, I could just simply look at the people, look at whom I like, and enroll them in the experiments because it's fun. Of course, such a behavior would be highly unscientific because it runs the danger of introducing severe bias into our sample, because I will select by certain characteristics. So this is not something that you want to do in a scientific study. Instead, we try to use random samples. So random samples, purely random samples, are samples in which every member of the population has the same chance of being included. So this is an illustration. Here we have the entire population, and then we just by chance select a subset of them And every single one of these a priori had the same chance of being included in the sample. What's important for that process is that members of the sample are chosen independently for each other. So even if I choose, let's say, in a family, the husband, the wife has the same chance of being included in my sample as if I had not chosen the husband as well. But she also does not have a higher chance than before. Random sampling is unbiased, if done right, but it also can lead to high sampling variability. So to improve on that, we can, for example, use something called stratified random samples. In stratified random samples, your sampling variability can be lower, and your accuracy of the inference that you later make can be bigger. What you do in stratified random samplers is that from the entire population, you select people, or you select certain subgroups of people for your analysis. This makes it also possible to do a subgroup analysis later on. But, as you might have guessed, the definition of these subgroups can also be problematic. It can either be hard to define meaningful subgroups for your problem, or it can be hard to actually get access to them. What kind of errors can we make in sampling? In this process of creating random samples of a certain size, we inevitably introduce variability in our data because we have not measured everything. If we sample multiple times, the result of the experiment or the statistical analysis will be every time slightly different. And we will talk about how to deal with this fact and how to still make conclusions despite this variability. So we have mentioned several of these terms before in a colloquial sense, but I would like to make sure that, that these terms are a little bit more solid in your minds. So variability is the variability around a true value. So for example, if we have low variability and low bias, then our inferences, if we sample multiple times, so if we create many samples from the same populations, they all cluster tightly around the true value. If we have high variability, then all the outcomes of our experiments still cluster around the true value, but they're substantially more spread. So limiting the variability of your sampling process or of your measurement, also variability can also be introduced to your measurement devices, can help us draw inferences. But there's always some variability in the sampling process that is also not possible to remove entirely. Where variability can, to some extent, also be taken into account in later on in the process of analysis, there's nothing you can do when you have bias. So here you have, for example, a situation where you have low variability but high bias. So you very consistently get a wrong estimate of the quantity you're interested in. This is, of course, not a situation in which you want to be. Here you have high variability and high bias. So for making inferences, such data is not very helpful. So because it's very hard to correct bias later on, you ideally want to build your experiment or your study in a way that avoids bias as well as possible. With this, I would like to thank you for your attention today, and I hope that this introduction to the basic concept of statistics will help you answer the following questions.